name is Dr. Esther Trufan, and in this video, we are going to explore electromagnetic radiation. By definition, the electromagnetic radiation refers to the transmission of energy through electromagnetic waves, which means that these waves have an electric component, and that's what you see in these blue waves, and a magnetic component, and that's what you see in the pink waves. When it comes to waves, especially waves of electromagnetic radiation, we mostly focus on two characteristics: wavelength and frequency. Wavelength, which is denoted with the symbol lambda, indicates the distance between two consecutive peaks or troughs in a wave. But this could be any two identical points on two neighboring waves. Frequency, that is indicated with the symbol nu or the letter n, the Greek letter n, indicates the number of successive wavelengths that pass through a given point in a unit time, and that unit time is going to be the second. So the unit for wavelength, because this is a unit of distance, is going to be the meter, and the unit for frequency is going to be the hertz, which is the same as second to the -1 or per second. When we look at the expression c equals lambda times nu, c is going to be the speed of light. The unit for speed is meters per second. The unit for lambda is meters, and the unit for frequency is per second. So this gives us an idea of how this expression is further enhanced by the fact that the units are the same on the two sides. And we have to keep this in mind every time we work with this formula, because that means all our wavelengths have to be expressed in meters, and all our frequencies have to be expressed in hertz or per second units. The electromagnetic spectrum is the range of all types of electromagnetic radiation, and it usually comes with two sides. There is the wavelength side and there is the frequency side. Both of those will have units indicated. Most of the time, these will be the base units associated with those properties. However, in some instances, the hertz may be changed to kilohertz or megahertz, and the meters may be changed for nanometers, especially if the spectrum is only showing a part of the whole electromagnetic spectrum. We can use this information about frequency and wavelength in a variety of ways. The easiest one is to simply compare different types of electromagnetic radiation as a function of their wavelengths or as a function of their frequencies. So here is a problem in which we are tasked to find the radiation with the shorter wavelength. And we have microwaves and X-rays. This means that we will have to look at the wavelength scale, which is the bottom. We need to identify our microwave range, and we need to identify our X-ray range. And then we look at the exponents associated with our 10. And we find that microwaves are on the range of 10 to the 0 to 10 to the -2. And X-rays are in the range of 10 to the -10 to 10 to the -8. Of these two, the shorter wavelength will always belong to the X-rays. If we are to compare the same two types of radiation on the basis of their frequency, we simply need to look at the frequency side of our electromagnetic spectrum and locate the two types of radiation on it. We have microwave with a frequency of 10 to the power of 10, and we have X-rays with a frequency of 10 to the power of 18. Of these two numbers, the larger number belongs to X-rays, and here we find that the higher frequency belongs to X-rays. As our original expression indicated, frequency and wavelength are inversely proportional, and if the wavelength is short, then the frequency will be high. Another type of problem that can come up in the context of electromagnetic radiation and the relationship between frequency and wavelength is the interconversion among these two properties. Here we have a light that is yellow in color. We have the associated wavelength as 589 nanometers, and the task is to determine the frequency associated with it. Step one is going to be to convert to the base unit of our property, and that is from nanometers to meters. So we begin with a simple prefix conversion. We have 489 nanometers. We're going to multiply this by a fraction. the bottom of which will have 1 nanometer, and the top will have 10 to the negative 9 meters. The answer will be 5.89 times 10 to the negative 7th meters. Once we have our wavelength in our base unit, then we can move on to the use of our expression to convert to frequency. If our formula is C equals lambda times nu, and we need to find the frequency, which is nu, then we can divide both sides by the wavelength. So it becomes C over lambda is the same as nu, which means that in terms of numbers, we need to find the speed of light, which is a known constant, that is 3.00 times 10 to the 8th meters per second. And we divide this by the wavelength in meters that we just calculated, 5.89 times 10 to the negative 7th meters. The meters will cancel, and the units will be per second or hertz. The number that we're going to get is 5.09 times 10 to the 14th per second or hertz. And with that, we answered the question related to frequency. We can do it the other way as well. In this problem, we have provided the frequency in megahertz, and the task is to determine the wavelength of the radiation. Step 1, convert to the base unit, which is the hertz or the per second. We start with 91.5 megahertz, and we multiply it by our conversion factor. On the bottom, we have a 1 megahertz, and on the top, we have 10 to the 6th hertz. This gives us 9.15 times 10 to the 7th hertz. And now we are in our base unit, hertz or per second. In the second step, we utilize our formula to convert from frequency to wavelength. If we need to determine the wavelength, then we need to divide both sides of the equation by the frequency. So C over nu is the same as lambda, which for us means that we have C, the speed of light, 3.00 times 10 to the 8th meters per second. And we divide this by the frequency in the base unit, which is 9.15 times 10 to the 7th per second or hertz. In this case, it is best to use the per second so that we may cancel these out and find our wavelength in units of meters, which will be 3.28 meters.